Welcome to the Killer Innovation Show, the longest continuously produced podcast in history. Each week, Phil McKinney brings you the insights and strategies to amplify your creativity and innovation skills. Here's your host, Phil McKinney.
Welcome to this week's episode. We have another guest. This is looking at some innovations in technologies that I'm going to guess most of you don't think a lot about deeply. Today's topic, we're going to jump into the weird sci-fi technology of quantum, and particularly quantum computing. Now, the technology behind quantum can be really challenging. You've got to be into physics and Einstein and quantum theory, etc. But today's guest does a phenomenal job of simplifying it so that it's understandable, and more importantly, as innovators, helping us understand what it means to take advantage of this technology and how to take advantage of this technology to solve the problems that, as innovators, we are challenged to solve. Today's guest is Scott Crowder. Scott is the vice president for IBM Quantum, and IBM is one of the leading companies doing work in the development of quantum computing. In addition to being the vice president for IBM Quantum, he's also the CTO for IBM Systems, Technical Strategy, and Transformation at IBM. So he's got a CTO role at the same time driving the technology, strategy, commercialization, transformation around quantum. And in this conversation, Scott shares how you can actually experiment on a quantum computer, trying it out with some of your own algorithms, how to learn about quantum computing and how to take advantage of its unique capabilities, etc. So you're going to want to make sure you listen to it. And at the end, I ask Scott the same question I ask all my guests about what technology, what innovation are they most excited about? And I put the extra restriction on for Scott that it could not be about quantum. What other innovation is he most excited about? And he gave a phenomenal, great answer. So you're going to want to listen to the end to catch up to that. So before we jump into this week's episode, follow us, hop on over to social media, follow myself, follow the show so that you keep up with what is going on. Like the show, give us a thumbs up, give us a positive review wherever you get your podcast episode, and share it. Share it on your social media, share it with your friends, share it with your coworkers. If you have a discussion around today's topic of quantum computing, quantum networking, quantum cryptography, if any of those topics are of interest to your team, share it. Have your team listen to it. There's a team at Pitney Bowes where they listen to the podcast interviews and they have the staff listen to them on the innovation team. And then they come together and talk about, well, could this be something that Pitney Bowes could take advantage of? So try using the show for conversation starters with your own innovation teams. And let me know if there's topics, questions, whatever that you think you and or your teams would be interested in hearing. Would love to hear that. So just drop me a note over at phil@killerinnovations.com. And with that, let's not delay any longer. I want to get into this interview. So let's hop over to the interview. Scott Crowder, Vice President of IBM Computing. Here we go. So Scott, thanks for joining us on the show today. Before we get too deep, because I've got a whole list of questions here that I've been queuing up when we finally worked out the schedule for you to join us. But give us a little bit of context. When we talk about the fact that you're leading the quantum, the VP for quantum efforts at IBM, give us some background on quantum, and then we'll jump into what is IBM thinking about doing about that.
Sure. So fundamentally, quantum computing is just a completely different information science than what we call classical. So most of what we've been doing up to now is classical information science, and it didn't really start in the 30s, 40s with programmable digital devices. It started before that. So, fundamentally how we, calculate using binary systems, hasn't really fundamentally changed until you hit quantum information science. So it's similar. We use similar concepts, but there's really some fundamental differences. So one of the fundamental differences that causes people to get so excited about it is that it scales non-linearly. It scales exponentially. So in classical information science, typically, if you want to double the number of states your system can explore, you add another bit. It scales linearly, and that's true if you're counting chickens with your fingers or you're on a digital computer. It fundamentally scales linearly. So, at best case, if I want to double the computing power or double the memory, I need to double the number of bits in the system.
So this is why, I've got a little bit of background, on doing high performance computing, the old supercomputer architectures that like the national labs use. And you go up, I was up in the INRA lab, Department of Energy lab here in Colorado, and they had just installed some new HP gear, which I was involved in back in my HP days. And the room sizes that they're getting into these supercomputers are massive because they literally, if they want to do better prediction of weather, they need twice the gear, which means you need twice the floor space to host that.
Right, absolutely. And the last, it's now like, I'm getting older. It's like, 70 years, 80 years has been like doing a magnificent job of Moore's law, et cetera, of being able to reduce the space, increase the energy efficiency of those bits. So you can jam more into a given energy envelope, a given, space envelope, but it's fundamentally linear. And the reason why people are so excited about quantum computing, other than the fact it sounds like sci-fi come to life, is that it holds the promise of scaling exponentially. So if I add a qubit to the system, every time I add a qubit to the system, it doubles the amount of state space that I can explore efficiently. So that adds up really quickly. So the number of qubits that equals the number of atoms on the planet Earth is in the hundreds. The number of atoms in the universe is like 2 to 350 or something like that. So if you get in the hundreds of qubits, with the huge caveat that they have to be of sufficient quality, et cetera, the state space you can explore is equal to the number of atoms in the known universe, which is a little bit mind-blowing. But that's the wonderful, wacky world of quantum mechanics that that allows that.
Well, that's a point though that I think a lot of people get confused, right? Because if you're at all involved in technology and you've been reading the press releases and you've seen this incremental of the count of qubits, right? Which everybody then says, well, it's got the word bit in it. So then they jump back to traditional thinking about what a bit is, and they're like, okay, well, they're only at 12 or 20. That's not enough to do anything with. What you're saying is no. You can't think about it as a bit being a single state, and therefore, you get to 100 qubits. Yeah. That's massive as far as the compute power.
Yeah. So just to get into the weeds a little bit, I know this is for quantum computing, for me at least, it's increasingly realizing how much I don't know as I get more and more into it. But just at a high level, quantum computing leverages the concept of superposition, which means that when it's in a quantum state, it's in a superposition of the 0 state and the 1 state. It's actually in one state, but that state is a probabilistic mix of the 0 and the 1 state. And then when you measure it, it collapses back to a 0 or 1 with a probability based on what quantum state it was in. So it's actually in a defined state. And because it's in a defined state, you can do manipulation of it. You can do programming, right? It's just that it's in a quantum state, which is a little bit of head blowing. So the fact that it's in superposition means that if you've got many, many qubits and they're all in superposition, when you take one operation, it affects the probability of all of those states with one execution. So it's not that it's in all states simultaneously, blah, 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 blah. Sometimes you hear that in the hype generation. But it allows you to do something parallel because of that superposition that has no classical analog. So that's one of the differences of quantum information science. So it is definitely a true statement that if you're at like 27 qubits or arguably at like 60 qubits, that you can simulate that on a classical computer today. So if you just stayed at 27 qubits, you could do something different and maybe better than a classical computer, but it really wouldn't be something that you can't do on a classical computer. When you start getting into the hundreds of qubits, that's where it's game over. If you're really truly doing quantum information science, you can't represent that state space on a classical computer. You just don't have enough memory. You just don't have enough compute. You don't have enough bits.
Well, you also don't have enough time, right? Because you hear all the calculations of what it would take to do the same for programs or problems that take unique advantage of quantum. We would be looking at massive amount of time if you try to do it on a classical computing platform.
That's correct. Although there's a huge caveat to that, which is it depends on how fast your quantum computer is, right? So, if you think of quantum computing, there's really three attributes. One of them is how good is the calculation, so quality. Like if your errors are too much, you're in the noise. You're never going to get there. Speed. We're not creating deep thought here. Like if your operation takes like a minute or even a second to run each operation, you might get the right answer if your quality is good, but you're going to have to wait 1,000 years. And what's the point, right?
That was the point.
And there's scale, which is we talked about before, right? So, to solve like more real world problems, it probably is going to take thousands of qubits to do that, just for the scale of the problem. So, big picture, the question is from a technology point of view, are you there yet on quality, speed, and scale? And the answer is no, we're not yet. So, ignoring all the hype that's out there in there, we're not there yet. We do have real quantum computers that people use, so it is sci-fi come to life. Absolutely true. We're making huge strides year over year. We put out ourselves put out a roadmap of what we were going to do in 2019, in 2020, in 2021, in 2022, in 2023, 2024, 2025, et cetera, et cetera. And we've hit every single milestone so far up to through 2021. So if we keep on that trajectory, yes, by the middle of this decade, we will have systems of sufficient quality, speed, and scale to make that crossover point between understanding how these quantum computers are going to be used for real world applications to actually using quantum computers to do something better than you can do on your best classical computer on the world.
So what are the big problems now? As you talk about that roadmap, right? You're saying, okay, mid of the century. What's the
middle of the decade?
Middle of the decade, not the century, decade. What are the big hurdles that you have to overcome to get there? From what is state of the art today in quantum to where the big problems are?
Yeah, so there's innovation across the whole stack. So I'll start at the bottom and go up. So you need to have qubits, which is the thing that holds your quantum state, to be as quantum and high enough quality calculation as possible. So there's a lot of innovation that needs to happen there. There's innovation at the system level for the speed. So like I said, you don't want to create a deep thought that takes 1,000 years to 48 or whatever the answer was, right? You need a programming environment that makes it easy for people to program. You need algorithms, so you need innovation in algorithms to new algorithms that can unlock use quantum information science to do math in a different way. And then you need applied research innovation. Like, now that I know I can do this math better, what are the real problems that people want to solve that can use this math to totally disrupt their industry? So you need innovation across the whole stack.
So what are some of those problems though that people are looking at that quantum, when you get all this, when you get the entire stack in place,
Yep.
What are some of those problems that are going to be uniquely advantaged in quantum?
Yep. So there's three types of math that we already know today based on people on a whiteboard proving that eventually they'll be better on quantum computing. One of them, which makes sense, is around simulating quantum mechanics. So because you're using quantum mechanics as part of your information science, it kind of makes sense that it would be good at simulating quantum mechanics. So things like simulating nature, chemistry, drug discovery, material development, et cetera, et cetera, et cetera, right? So that's kind of an obvious fit, that it would be good at that kind of math. The second kind of math is around data that has unique structure. So there's a famous algorithm called Shor's algorithm, which is basically a factoring algorithm, which is the one that freaks out three-letter agencies and et cetera, because it was proven on a whiteboard that if you have a big enough, fast enough quantum computer, that you can do factoring much more efficiently than you can on classical. And by much more efficiency, I mean like in the matter of like a day, as opposed to in the matter of like the life of the universe efficiency. And the reason why people care about that is factoring is used in a lot of our cryptographic solutions.
Well, this does get into a lot, because there's a lot of work I know I'm familiar with on quantum cryptography, right? And how do you build cryptography that's resilient to quantum, right?
Yep.
So there's a whole science in that end. And then the flip side being is that if you don't get prepared when quantum comes online, any form of cryptography you have today becomes pretty much useless, right?
Yeah. So the good news is that yes, we have demonstrated classical quantum safe cryptographic methods. A lot of them based on lattice methods, and I won't go into gory detail. But they exist today. So they're known algorithms that are going to be harder for quantum computing to break. Right. The other good news is that it'll be some time before quantum computers can do that.
Right.
So there is time.
Yep.
The challenge is that changing cryptographic methods is time consuming, and most industry aren't exactly really agile with their cryptography. I'm being nice. So what we tell people is that you need to think about like what are the data assets that you have that are very sensitive, that are going to be on a platform that's going to be around for a very long time.
Yeah.
And for those, you should start thinking today about, do I need to do something before NIST declares a standard? Or if it doesn't really fit into that category, it's probably better to wait for NIST to declare a new standard and then go after it.
Right.
Yeah. The other thing it's not just Shor's algorithm for that data with the structure. There are other types of math like machine learning. This falls into machine learning too, like quantum support vector machines, where you can leverage the higher dimensionality that quantum provides to basically pull out the structure in a different way than you can't do classically. That may have a significant advantage for a lot of machine learning. And then the third type of math that quantum is going to be good at is search problems. So this is something called Grover's algorithm. It's applicable for optimization problems, Monte Carlo types of problems, those kind of things. There's a lot of excitement there because those are very easy to understand across a lot of domains. The only challenge there is that the advantage is polynomial for that. What that means is that there's a significant advantage there, but it doesn't scale as fast as those other two examples that I gave, which are exponential advantages. So, days to the life of universe, polynomial is more like, day versus month or something like that.
Yeah.
So we were very excited about those two, but we really think that, the data with structure, especially in machine learning and things like that, and the simulating quantum mechanics, quantum nature are probably the first two that are going to become like real, I can do something on a quantum computer that I just can't do on a classical computer, and probably will never be able to because of the way it scales.
So Scott, a few minutes ago, you were talking about, what's real, and that IBM has this roadmap, what's going to happen before the middle of the decade.
Yeah.
But also you mentioned that there's a lot of players out there, and there's been a lot of press and people claiming that, they're the quantum leader because they've got more qubits, right? But you point out that it's not just the number of qubits, but quality and et cetera, right? So, there's a lot of interest in this space, like Microsoft's in it now. You've got, Google in it. You've got the amount of university research in this space is exploding. Because I get requested from universities all the time to throw a little money their way to help fund, because it's expensive research to in this space. But what's the landscape look like? There's just the amount of effort into this space is just, it's growing maybe exponentially, just the number of people that are trying to rush in for a land grab here, I think.
Yeah, I think that's true. And I think, it hasn't been, I think the industry, there's a couple trends in the industry, I think, that are, I think from a understanding the landscape is important. So the first is, quantum information science slash, quantum computing versus quantum annealing. There's a company called D-Wave that's been, in the industry for quite some time that is initially was focusing on quantum annealing, which is for a specific kind of problem using quantum mechanics to do annealing, which is an HPC kind of approach, using quantum tunneling as opposed to simulated annealing, which is a classical approach. So it's kind of like a apples and oranges kind of compare. Right. I won't say too much on that other than it's there have been a lot of claims, I think, in terms of people actually using it in production. It hasn't really cracked that yet. Obviously, our opinion is that getting to the exponential speedups of true quantum computing is the way to go, because it really is something you can't do classically versus quantum annealing. There may be a speed up, there may not be a speed up, but it's a little bit less separable. I'll just say it that way.
Right.
And then the other thing that's happening from a landscape point of view, which I think is causing a lot of confusion, is that there's a lot of talk about quantum-inspired algorithms, which, not to be too glib, but from our perspective is like classical heuristic algorithms. So if you asked us, what is a quantum-inspired algorithm? It's like, it's a classical heuristic algorithm. Like, go talk to our AI people, because that's what they do on a daily basis.
I don't know. When you said that, I've never heard the term before, quantum-inspired. It sounds like someone from the marketing department got involved, and they're doing a little bit of a spin in order to get the quantum buzzword into the name or something.
Yeah, I mean, I think it's real, right? So I mean, people have been developing classical heuristics, leveraging insights from scientific,
right,
for a long time. I'm not disputing like the value of the algorithm,
right,
but yes, that's our sensitivity as well. It certainly, some other vendors in there have crossed the line from our.
Yeah, well, it's interesting because that's always we've seen it in any form of major disruption, something that's a fundamental architecture change. People kind of hop in. I mean, I think it was 3 years ago. For 20 years, I've done this annual prediction of going into CES, what buzzword is going to be the hot buzzword, right? And like 3-4 years ago, everything was AI. Didn't matter what, I've got my AI empowered pen. I've got my AI empowered toothbrush, right? AI was everywhere, which means the marketing department was just trying to punch the buzzword bingo card on dropping the term versus, but it's not just a new thing. It's going on for forever, right? And I think it's a little bit of, it gets people excited. People are saying, look, what is this AI thing? And they learn about it and they see about it. I think quantum, we're kind of coming out of that, and people are kind of saying, okay, when's this going to be real? When is this thing, really, when is this thing really? And from that standpoint, should consumers even care, right? Is quantum going to be something that, as a typical user or small business, is quantum something that they even should have on their radar screen?
So the way I would frame it is, if we do our jobs right, that the corporate research and corporate, like chief innovation officers, CIOs, should be aware, because it takes time to introduce a new technology into their portfolio. Mm-hmm. So a lot of times you get equivalent examples of like how long it takes to take GPU technology and get it into production. So it is potentially disruptive enough. The other math problems that I mentioned, do have significant, real life application, that if we do our job and deliver the technology, in the next, 2 to 4 years, because the middle of the decade is 2 to 4 years away, that, those types of people need to start paying attention today. From a consumer perspective, if we do our job right, we're going to make this technology consumable enough to people who are building models that are enabled by quantum, like an AI example, machine learning example, that the consumer doesn't need it. It's like, does the consumer understand, when they're like, digitally taking a picture of a check and sending it in, that what the AI is underneath of that? Are they going to care whether that's like a quantum enabled model that's a little, like 2% more accurate than the classical one? Probably not. But hopefully, in the space of like the simulating quantum mechanics, consumer will end up with I'm going into like waxing poetic stage, but seriously, like getting into like lighter weight airplane wings because of material development, or improve personalized medicine because we can do a better job of pulling structure out of smaller sample size clinical trials. These are the kind of things that the underlying math that quantum computation should be able to do a better job of classically can have a real world implication on society and customers. But the consumers themselves will probably not like see a quantum computer doing that. It will be like in the background doing that. If that makes sense.
I think for a lot of consumers, that's today's technology even, right? Do they really know the AI algorithms that are trying to prevent credit card fraud?
Right,
all they know is maybe they only have to swap out their credit cards twice a year versus 4 times a year in the past because of the fraud situation, right? Those types of things. The fraud situation is a little personal, given I've been dealing with credit card fraud here recently personally. So we were talking before though about also, you talked about the IBM roadmap, and if you unwind, right? I started off my even college on an IBM 360 158 back in the day, punching cards and doing my early COBOL and Fortran and Watt 4 and Watt 5 programming, etc. But you think about back then, there were a lot of companies trying to figure out how to make a general purpose computer that businesses could take advantage. You had RCA, you had Univac, you had Burroughs, you had all these players. IBM won, right? 360 and the 370 platform, that kind of cinched the deal. IBM figured it out. It was the compatibility, the ability to take long-term investments and have an architecture that could support multi-generation. Today, we got a lot of players in the quantum space. What do you think it's going to take to kind of bring down and define what a winner looks like in this space?
Yep, I think it's 2 things. Well, I'll say 3 things. One of it is clearly somebody needs to develop the technology. This is not a trivial thing, so there's a huge amount of innovation left to do in the infrastructure and in the software stack in order to basically provide any value for quantum computing over classical. So that's number one. And that is resource intensive, brain power intensive. It takes, both money and like really, really smart, innovative people to do. So that's number one. Number 2 is it needs to be made easy for it to be consumed. And this, is I think a difference between now. There's a lot of analogs between, like you said, the computing in the 50s, 60s, and where we are in quantum computing. I think one of the things that is different is that we really have developed the software stack and the internet, and we can make this technology more easily accessible to a lot more people, a lot more rapidly. And one of the fundamental things about our program is to really do that, to do 2 things. One of them is to not make it more complex than it has to be. There's a lot of things about quantum information science that is extraordinarily complex and hard to understand. But if you're a model developer, we should be hiding most of that complexity from right. It should be an API call to a quantum-based solver as opposed to a classical solver, and all you should have to do is make an API call to one solver versus the other solver.
Right.
You describe the problem exactly the same way. It's just you're calling a different solver, right? So if we do our job right, that's what we're going to do. And then the third thing around that, and this is both from our really strong belief it's just a right thing to do, but it also isn't completely without our self-interest, is drive adoption, right? So make the technology available to as many people as we can, as long a tail as we can. Let's use the cloud. Let's use Python, existing programming languages, and just make it available to as many people as possible. Work with as many industry clients, academic clients, research institutions as we can to help drive the adoption of the technology. Because the part that's more of a self-interest point of view is we strongly believe we're going to be the first to market with quantum computers that can do something better than a classical computer can. But we want to shorten the time between the time we bring the technology and the time that it's actually used.
Right.
And the way we can do that is really focus on driving adoption, not just from a societal good point of view, because we also strongly believe that, but also from the point of view of, frankly, we're going to make more money if we reduce the time between the time the technology is available and when people can actually use it.
And so because today there are some quantum computers that are available on limited basis for cloud for experimentation. Is that so? So what I'm hearing from you is you think that is really kind of the early go to market. It's not going to be the old days where everybody's putting one into their data center, but really to get that early adoption, people want to touch and use and validate that it solves a problem uniquely or better before they jump in with both feet. So it's interesting from the standpoint when you really think about a try before you buy model, right? Of today's very complex technologies.
Yeah, so we've got over 20 quantum computers available through the cloud today. We have quantum computers deployed in Germany, Japan, and the US. And we've announced that we're deploying a system in Canada and South Korea as well. We've got kind of two levels. One level is more open, try, and it's really to drive education, understanding what quantum computing is, how do you program a quantum computer, what is it good for, kind of thing.
Right.
And then the second is, we have higher quality, higher capacity systems that we provide to our research institution partners, our industry client partners, our academic partners to do more deep research, to really understand this is what it's going to take to take quantum computing and deploy it in my industry, or for my research at the national lab, or for my research at the academic institution. So we've got about 400,000 registered users for our more open platform, and we work closely with, now it's over 175 industry, academic, and research institutions more deeply, and exploring quantum computing, how it's going to disrupt people's industries, how can it get leveraged to do cutting edge research.
So you talk about that, because I knew you had some of it, but I hadn't heard the numbers before. So you've got to have like one of the largest user bases then of people experimenting with quantum, bar none.
Yeah, absolutely. Yeah. Yes.
Wow. That is.
So absolutely. Yeah. And obviously the other thing that I think, is maybe a little bit non-traditional for a large company sometimes is that, I think we've done a pretty good job of, from day one, focusing on adoption and making the technology available. And two is really partnering deeply, not having the attitude that we can do everything ourselves, but having the attitude that for creating a new technology, it's not a one institution thing. So we work really closely, like I said, with research institutions across the globe. Places like Oak Ridge in the States, Fraunhofer in Germany, University of Tokyo in Japan. As just examples of like really having deep partnerships. Cleveland Clinic is another example in the U.S. that's really more domain specific.
Right.
And we do that for two reasons. One, like I said, because we don't think we can do it alone. And second is, again, for the self-interest part, we really believe that if we understand the problems better, we'll understand where the math can be applied to the problem, and we'll just create better technology, for those use cases.
Well, I think the deep partnering, we could have a whole separate conversation on that, because as these technologies, as innovation accelerates, the pace of innovation is moving at such a clip that also drives the cost to innovate is also getting to be pretty significant, right? I mean, before we started the show, you and I were talking about, the lovely experiences of being inside large organizations, which have great resource pools, but getting to those resource pools when you need them can be a real challenge, because these things can be very expensive to pull together, these very complex pieces. And so therefore, co-innovating, partnering, deep partnership, as you call it, almost becomes really what I would call the new skill set that innovators need to have. Because if you think you can do it alone, it's not going to happen.
Yeah, I totally agree. I totally agree. And we've been, I think, I'll say lucky. Obviously, there was some design there, but we've been lucky to have like really strong support from every part of the company, in doing this, and the knowledge that this is not, this is a medium-term play. This is not a next quarter time type play, right? So, we've clearly got our metrics that we need to keep hitting, both internally and externally, because we've been very, very transparent about, our roadmap. We're going to release this size system, this year. We're going to hit these specs this year. We're going to release these capabilities this year. In a way that is a lot more transparent than like a large company would typically do.
Right.
But honestly, in this kind of emerging field, again, for two reasons. One, because from a societal point of view, I think it's good for people to understand where we really are in the technology, because it's easy to get so excited about the sci-fi come to life that it kind of loses the subtext message of like, and this is what we need to keep doing so that it provides value. But also because, like you said, there's so much hype in the industry that, from our perspective, the best way to deal with that is just lay down exactly, this is what it's going to take for quantum computing to get real. It's not like our grandkids' lifetimes; it's like our lifetimes. But we still need to do these things and demonstrate that we've hit the roadmap, because there's a lot of different opinions out there on, like, you'll hear like quantum computing is already going to impact your life today. You hear that a lot in the market, and you hear in the market like it's something that's going to happen like in the next millennium, right? So there's like there's a wide distribution.
Right.
So we're trying to like keep like fact-based, like here's the roadmap you need to get there, and here's where we are on the journey as the best way to kind of to solve it.
Well,
It doesn't always solve it, I'll be honest. It doesn't always solve it.
Well,
anytime there's a newspaper article that comes out.
But I think your point, though, is the fact, though, that your model of making it available, both with your deep partnering, but also allowing people to have access to a more public exposure of this, to allow people to kind of look at it and try it and kind of try to understand it. Because while you're working on that roadmap, the ability for people to kind of get their heads around this, and look, I've been challenged trying to explain quantum to my board of directors, right? Because it comes up in conversations with what's its impact on cryptography because of network technologies in the industry that I'm in. But giving people that long lead time so they can kind of get their heads wrapped around it and think about it before it hits is really important, because this is not just the next generation of an x86 processor or next generation of a GPU. It's not just the next of the great things we have today. This is like, whoa, totally, you got to think about this differently.
Yeah, yeah. What I'm most personally proud of is like we've gotten to the point where we've got like, nobody in IBM marketing at all was involved. Like in a news story coming out of like Cleveland about like a 17-year-old high school student who's like super excited about working with Cleveland Clinic, on quantum computing. That's using our like on the web, digital training, and has got like sold on quantum computing and is excited about moving to Cleveland Clinic. Or one of our partners like NC State, like meeting with the state of North Carolina educational system about how to teach quantum computing, talking about like the work that we've been doing with third parties to really bring like a full year course on quantum computing to high schools, and using that as, again, we're not involved, using that as an example of how to do it. So those are the things I'm like personally proud of. That is beyond it's kind of like the societal good part of things.
Yes.
And we've made a really big effort also, and the team ethos on this is, we have an opportunity to shape the quantum workforce of the future.
Yep.
Because it's so exciting, as this sci-fi life comes to life, so people are interested. So let's purposefully go after those folks who are underrepresented in STEM and
Yep.
make sure that we're getting them excited about quantum computing, et cetera, et cetera. Not that it's not important in general for STEM, but I think we've got a unique opportunity because this is so new to really shape the workforce in a way that generic comp sci or generic pick your field is harder. So that's been really cool too to see.
Well, it's also, I think it plays off of the Wayne Gretzky quote, right? Don't if you want to win in hockey, you need to be where the puck is going to be, not where it is today. And you look at where the capabilities that quantum is going to bring to the society, into the world, is going to be so impactful. For kids today, that's the puck they want to be at, is really understanding quantum to be ready when these roadmaps become, I'm saying the material today, but it's just like the early days of mainframe computing. The rate of improvement over each generation, or each generation of traditional processing architectures and current information theory. This is the new leap. Kids today, this is the puck they should be aiming for.
Yeah, I mean, the way I think about it is, as we release better and better quantum computers, it's going to unlock more and more use cases.
Yep.
So it's not going to be like, one moment in time is going to be, okay, this is the time quantum computing took over the world. It's going to be, evolutionary. And as we, middle of this decade is when we're going to get the first swath of use cases. But over our lifetimes, it's going to get like larger, just like it happened in classical computers. The power of the capability of them is going to suck in more and more use cases over time, and it's going to keep growing.
Yeah, like me, my research was in computer graphics animation. Well, when I was starting out, I was doing single frame renderings off of an IBM mainframe. And now you look at what you can get from an NVIDIA GPU with light shading and everything. It's that kind of progression, but I think it's going to be even more. And I think, the question I asked earlier about what the use cases are, we think we know these use cases. We have no clue. Some really smart kid who's probably in grade school or junior high is going to unlock some use case that we never anticipated when they're doing their research studies. That is absolutely going to be transformative. And that's the exciting part, right? When you think about creating an innovation that is a fundamental, foundational platform that others are going to take and innovate on top of. That's the power of human ingenuity. I'm always amazed at it. Always amazed at it.
Yep. Yeah. And it's also really friggin' cool. So, the fact that, your qubits are like at temperatures, like the order of magnitude is farther away than, so the order of magnitude temperature difference between here and outer space is smaller than the order of magnitude temperature differentiation between outer space and where our qubits are at. Because that kind of thing that is like, it's like one of the coldest places in the galaxy is in a quantum computer. So there's lots of like really cool stuff that's, obviously attractive also. I mean, I'll be honest, it's there is an attraction just to doing things that sound like sci-fi, right?
Yep. Yep. So, hey, Scott, as we wrap this up, I always wrap up the interview with one question. So, what innovation? We're not going to mention quantum because we've just spent the last 35 minutes talking about quantum. But what innovation other than quantum are you most excited about?
So this isn't really one particular technology innovation area, but I think there's still a lot of innovation left, from the increased bandwidth that's out there now. And it's not like one technology. I think it's more about leveraging it, re-architecting solutions, et cetera, et cetera. I still think there's a lot of innovation there. Like people call it the edge, 5G, et cetera, but I think it's more about leveraging the large amounts of data and where it's located to deliver better solutions. So I know that's not a one-word answer, for innovation, but I think there's a lot of opportunity out there.
Well, that actually is a great answer because it's right in my backyard, given the work I do on broadband bandwidth and fiber optics and speed and pace of the technologies there. So, hey, Scott, thanks again. Really appreciate you taking this time out. I think that was a great conversation and really appreciate it. I'm sure the listeners are going to love this. Just mind expanding, thinking about things that are coming that as innovators, we can all begin thinking about what would we do when this comes available and what kind of problems could we solve with this in a unique way. So again, Scott, thanks for joining us today.
Oh, my pleasure. Anytime.
So what problem are you thinking about that might be able to be solved by quantum computing? I really got interested in Scott's discussion around optimizations. So there's a whole variety of optimizations. If you work at a facility that does logistics, you're shipping packages or entire containers on ships around the world, optimizing packing, unloading, etc. Quantum can actually optimize that loading and offloading to actually improve the pace through your ports, etc. That's interesting because look at the supply chain challenges that we are facing today. You can also do optimizations of airlines and therefore become more efficient, requiring less planes in the air, less pollution, less issues with regards to global warming. There's a whole variety of these optimizations that I'm really intrigued about. Now, many years back, I was the CEO at a supercomputer company that was a spin out from the University of Illinois called Terraplex, the Teraplex. And in fact, Business Week did a few articles on us. You might be able to find them. I don't know. I haven't looked. So I have a little bit of background in using supercomputers for these kinds of optimizations, particularly around weather prediction and around things like that. And those were interesting models, but you just threw more compute, more processors. You did these massively parallel supercomputers where you put a lot of processors in them, and then you rewrote the algorithm so that they ran simultaneously on thousands and thousands of processors. Quantum is completely different. And what it can do to break through on optimizations, I think, is going to be one of the early use cases that is going to have some of the biggest impact. But I'd be interested in hearing your thoughts. What problem are you thinking about? What problem are you working on? What problem is your organization facing that quantum potentially could solve? And take advantage of what Scott and his team are doing at IBM by hopping over there and trying it out. You can learn about quantum computing. You can actually experiment. And look, IBM does not pay a sponsorship. I'm not here promoting them because they're asking me to. They have not asked me to promote the program. But I just think it's interesting. I think the technology is something that all of us need to learn about. And for me, particularly for my kids and my grandkids, because like I said in the main segment, it's like kind of the Wayne Gretzky quote, you want to be where the puck is going to be. And quantum is clearly where computing is going to go in 5, 10, 15, 20 years. and to prepare that next generation of people who are going to work in this space, it needs to be around quantum and getting to that and learning about it and experimenting with that. And I think IBM's got a great approach to making that broadly, publicly available. So check that out. As we wrap up today's episode, I want to hear from you what you thought of it and also what topics, guests, interests you have that you think we should have on the show. So drop me a note, phil@killerinnovations.com, and I'll get that email. Andrew, who's the associate producer, and I will talk about it. We'll reach out to your suggested guest and see if there might be a fit to have them on the show. So again, we depend on you to let us know who potentially would make for great guests. So drop me a note. Also, just as a reminder, we're here to provide you with the best possible content and to make that available on a regular basis so you can plan on it. You can add us to your subscription so you just automatically get the show each and every week. But what we ask in return is help us grow, help us attract more subscribers, more people listening to the show. Pass the word, let people know about it. If there's a guest or a topic that you found especially interesting, let us know and give us feedback. Positive or negative, we are open to both. Negative allows us to improve. Positive, it's always good to hear positive feedback. As we are now into season 18, we are in our 18th year of producing the podcast, and we love being here every week. We greatly appreciate your time out of your busy schedule to be here and being part of this conversation, and we look forward to continuing for many, many years to come. So with that, we're going to wrap up this week's show. We'll see you next week here at Killer Innovations. Talk to you later. Bye-bye.
Podcasting nonstop since 2005, this has been the Killer Innovation Show on the Innovators Network.